Hello, everybody again. We have quite a few questions, and so I'm going to ask the panelists that they can ask their first couple questions, and then we'll keep going. We're going to start with Heather. Heather, please.
Thank you so much, Dave, and thank you, Jihye and Brian, for your expertise and knowledge on PPP today. Dr. Park, I actually had a few questions for you to start. Can PPP be used in real-time mode, and do we have the precise ephemeris and clock correction for this?
It's a good question. So let me share my screen and revisit one of the slides I used. All right, so this is the summary of the tables I have related to the satellite orbit and clock correction product. So as I mentioned earlier, we have the broadcast product from the signal in space, but there are several products produced by the IGS, the agency, associated agencies, and then IGS collect those products and make it available to public. So as you see here, there are some latencies. Obviously, it depends on the accuracy you want to achieve. So for the real-time application, if you want to achieve this high accuracy solution, maybe the broadcast is not the option, because you see this accuracy of the orbit is 100 centimeter, which is pretty significant for this high accuracy solution. The satellite clock offset is like a 5 nanosecond. The 5 nanosecond, if you convert it to this distant wide, then we just multiply by the speed of light, which is like 300 million meter per second. So that makes about like 1.5 meter approximately. So that is the expected error. But ultimately, there is another. So when we use the high precision solution, and we want to use a finer, but you see that there's a latency of 12 to 18 days. So it's not ideal for the real-time application. One option you can do is the ultra-rapid orbit and the clock product. That is the based on some prediction and the observation. So it's available real-time. There's no latency. The orbit precision accuracy is much greater. It's 5 centimeter. And the satellite clock correction is 3 nanosecond. It's a little bit better. It's about like a 90 centimeter, like 1 nanosecond would be about 30 centimeters of accuracy. So it's about 90 centimeter. It's still not the greatest. However, technically you can use a certain level of accuracy by using these products.
Thank you, Dr. Park. For my second question, I was wondering what the benefit is of using one method over the other, for example, RTK versus PPP-RTK. For example, it might depend on the required accuracy level and the surrounding environment, but how can someone easily make that decision? Does one significantly outweigh the other?
That's another good question. The difference between this conventional RTK and this PPP-RTK is like a matter of the available infrastructure. Because the conventional RTK requires like one fixed reference station. And if you think about this conventional network RTK, then you need the one reference station and also the surrounding network GNSS stations to create the solution, the corrections. Then the PPP-RTK, the basic concept is the same, that you have some correction information from somewhere, and the user use this correction information to reduce their error. But if you compare between this conventional RTK and the PPP-RTK, the conventional RTK requires more direct link between this reference station or the network to the users, while the PPP-RTK is kind of like a service provided from the space. Then the user or a certain like a bigger, wider network, then the user can receive the correction. But the thing is, like a network RTK or the conventional RTK may provide a higher accuracy than the PPP-RTK, because the PPP-RTK may, like expected accuracy could be a few centimeters, But depending on this the condition, but the RTK could provide like a 1 centimeter or even millimeter level of accuracy. But certain case, something like in a remote area that has a lack of the dense GNSS network infrastructure or like offshore navigation, then the PPP-RTK would be the better option, probably the only option.
Hey, Tom, do you have a question?
I do, thank you. So my name is Tom Meyer, and I'd like to direct my questions to Brian. Brian, to a practicing surveyor, PPP really looks a lot like OPUS in the sense that we're going to get RINEX files or some equivalent out of our receivers. We're going to then just go online and submit these to some processing service that does looks like a black box, and then it returns coordinates and uncertainties. So under what conditions would I use one over the other?
Thanks for the question, Tom. Yeah, it's a really good point. And the user side for the post-processing scenarios seem very similar. But one of the important aspects to consider is that OPUS currently is using a differential relative processing technique, while PPP is using this standalone yet precise point positioning technique. So that means that OPUS is applying constraints from reference stations, while PPP is not constraining reference stations and instead only constraining satellite positions. So if the user is operating far outside of this GNSS reference station network, like the NOAA network, for example, they'll quickly run into limitations for that differential processing mode of what's done with OPUS, because that requires mutual satellite visibility at each end of your baseline. For example, there are also some additional processing considerations when you do long baseline differential processing. But in those scenarios, PPP is a great alternative, or even potentially the only option if you're wanting a high precision global position after that initial convergence period is met. And one last thing to follow up on is that PPP is typically a pretty good validation tool, even if you're required to process or GNSS measurements through OPUS. It's always a good idea if you would like to check those OPUS solutions against something else, to use PPP, for example, if you have a sufficient duration to process those through the Canadian PP tool.
Okay, thank you very much. And to follow on with that, if I'm wanting to use GNSS for control, I would naturally want to create a network and come up with a network solution. Can I use PPP for network solutions for like control networks?
Thanks for the excellent question, Tom. Yeah, that's a really interesting point for PPP, because, like I mentioned before, we don't have that direct connection to some reference station like we do for a differential processing technique. However, there's an entire aspect of PPP which we didn't cover in our talk really, and that's the network PPP side. So our discussion was mostly or I guess entirely talking about the PPP user rather than the PPP network. So the PPP network is responsible for estimating those parameters like the receiver or the satellite orbit and flock that is then used by the PPP user. So to answer your question, yes, there is a PPP network side that is done typically by analysis centers in order to then estimate and give information to the PPP user. I think the important distinction there is that when we're casually talking about PPP, it's almost always implied that we're talking about the PPP user, which is a non-network solution, even though it's relying on satellite information estimated from some reference network.
All right, thank you. Karen, you got a couple questions?
I just have one to Brian. This is Karen Meckel here. How long would you need to occupy a point to obtain a position with kinematic PPP?
Thanks, Karen. Yeah, that's a really good question, because I think a lot of us are more familiar with RTK or network RTK, where there essentially is no initial convergence period. Integer ambiguities can be estimated with a single epoch of measurement data, right? But for PPP, we don't really know what those ambiguity values are at a high precision until we've accumulated enough measurements. And so to put numbers on that, typically the free convergence interval can achieve meter level, sometimes even several decimeter level precision. And then after the convergence period is achieved, we can get down to that centimeter level precision. The important part to your question, though, is asking about the occupation duration to get to those levels of precision. And for the kinematic PPP case, those precisions can be achieved immediately. So that meter level precision before the initial convergence is achieved, as long as you're okay with that, you could operate that way. Otherwise, if your requirement is to be at this centimeter level precision, you would have to wait for that convergence time to elapse. In the talk I gave, I showed a few examples with single system GPS only flow ambiguities, and that convergence time is around an hour or less typically. And then that can be improved down to half an hour or less for the multi-system cases, and then 15 minutes or less for those multi-system integer ambiguity resolution cases.
And does your collection rate matter? How long it takes to do your observations?
That's a really good question. The measurement rate is less of a factor on that initial convergence interval compared to the satellite geometry. So going from like a 1 second measurement rate to a 30-second measurement rate, you'd expect things to be much better with 30 times the measurements. However, those 1 second measurements aren't really contributing a lot of new information to your model, because receiver satellite geometries are very similar between those consecutive epochs. Where the high rate measurements really help is when you're in highly dynamic scenarios, and would like to do some screening for your measurements for outliers, as an example. Hopefully that answers your questions.
It does. Thank you, Brian.
Muge, you have a question or two?
Oh, yes. My questions are for either Brian or Jihye. What is the Galileo High Accuracy Service coverage area?
I'll take that question because I have a nice slide showing this coverage area. So let me share my screen again. So here is the Galileo High Accuracy Service, the service area that's published from one of these recent publications, showing that the test, like they just indicated the use of like core area. As you see that the test stations and estimation station, it's like phase cycle bias estimation stations. They are concentrated in Europe because this is a European service. However, they had a lot of like good distribution, relatively good distributions of these estimation stations and test stations worldwide. So they try to provide the service worldwide, at least like in this near this major continent. However, there are non-service areas indicated in here, like East Asian area, certain area. But I do know that they try hard, like working on expanding the service area, like anywhere in the world. So having those test station, like estimation stations, that is the effort for this next phase. That they just try to provide all the services, all the service to the other area as well. So here is the current service area, but in the future, it could be expanded better, and also the expected accuracy or performance would differ based on the distribution of the stations. So obviously, the European side would expect like a higher accuracy than the others. Hopefully, it answered your question. Okay.
Yes. What are some examples of non-ideal PPP conditions?
That's a good question. So, as Brian mentioned, the PPP, the downside of the conventional PPP would be the convergence time. So sometimes it goes up to like a few hours, and it like could be still tens of minutes. So when we really need the real-time applications with this limited occupation or data collection time, like something like a UAV-based surveying or data collection kind of applications, maybe the conventional PPP would not be the best option. Or like something that requires really high accuracy solutions, something like a cadastral surveying that requires like 1 centimeter or even millimeter level of higher accuracy, then probably we would recommend like other ways, something like conventional relative positioning, like static relative positionings, rather than the PPP condition, as long as there's available infrastructures like a GNSS network.
Thanks.
You're talking about convergence time. I got one for Brian, which relates to what was just discussed. So how long are these convergent times to reach a centimeter level position? Brian, I believe you showed the slide with that on, saying about an hour or so. So maybe a little bit more discussion on that.
Thanks, Dave. Yes, I can elaborate on that a little bit more. I started my talk off with showing the GNSS positioning spectrum, but even within the topic of PPP, we have the spectrum and many flavors of PPP. So there's, the traditional or conventional PPP with flow ambiguities. Then there's been efforts in recent years to do the same thing, but with fixed integer ambiguities. And then kind of the most state-of-the-art approach is PPP-RTK, which is combining different systems and frequencies together, also using integer ambiguity resolution for PPP. And on top of that, applying some regional atmospheric information to further strengthen the PPP user's performance so that it can approach something more like RTK. So those initial convergence times depend on so many factors. It's typically best to evaluate your whatever PPP software you're using for multiple stations across multiple days, distributed geographically, in order to understand what those convergence times are. Typically, I'd say less than an hour is fairly common under ideal conditions for conventional PPP. But the slide I have up here is showing additional improvements from that by using constrained ionospheric information. So this study, which feels fairly recent to me, but I guess it's more than several years old now, evaluated North Carolina GNSS reference station network, something that would be more recognizable as like a real-time network than RTN, but extracted ionospheric information for the PPP-RTK user in order to constrain different precision levels for the ionospheric information at the PPP-RTK user end. So the figure on the right side is showing the time to first fix rather than the convergence time, because now we're doing fixed integer ambiguity resolution. And when no ionospheric information is provided to the user, you're at around 30 minutes, or a little bit less, to get those fixed integer ambiguities. And then as progressively more precise ionospheric information is provided, that fixing time, or time to first fix, is reduced with the most significant improvement after around 5 centimeters or so for that precision of the ionospheres. And if the ionosphere is completely constrained and estimated with a very high precision, it can actually be fixed by the PPP-RTK user and reduce that convergence time down to just 1 or 2 epochs. That answers the question.
No, and it does. And I do recognize that network because I live in North Carolina. So that is North Carolina's is their GNSS/RTN network. So I guess a follow-up question to that, and one of the things I was thinking is, well, if PPP is so good, then North Carolina wouldn't need their network. Although looking at this, PPP can only really be that good as their North Carolina's network, as long as PPP uses the information from the network to improve its atmospheric conditions and geometry conditions. Am I understanding that correct? I mean, North Carolina has 99 cores in their operations, and they have a real-time network that's very good. But obviously, if they could decrease their infrastructure, they would. So can you comment on that a little bit?
Thanks, Dave. That's an excellent question. It seems like a lot of what we have talked about is focused more on the conventional PPP, which is operating at more of that global scale. It, at first glance, would appear that you don't really need this dense of a reference network. But actually, any sort of regional high density reference station network like what's shown on this slide, really just helps you move further along to the right side of this figure where we're reducing that time to first fix so that we can achieve a very high precision solution immediately rather than having to wait. So yeah, to answer your question, that infrastructure doesn't need to go away. In fact, more high density reference station networks would be preferred so that these PPP-RTK users could leverage that high precision information as constraints on their positioning software.
Okay, yeah, it's interesting because there's a lot of networks around the country that if someone in the United States decided to really use, like Canada does their PPP network, it would be interesting to see how that could, for where it would improve it. Clearly, North Carolina would be good, but Ohio has there's a lot of states that have that. Let's see, Heather, you have another question for?
Yeah, I actually have a question for Brian this time, kind of a more general question for users that may have this question when thinking about making this adjustment to PPP. Are there cost benefit resources that are readily available for surveyors who might want to make this transition, or should they conduct their own research entirely by themselves beforehand?
Thanks for the question, Heather. I don't have a great response to that one because I think it's typically a little hard to quantify ROI or return on investment for some geospatial technologies. And typically it's a little easier, at least for me, to just think about kind of the basic limitations for each technology. So for example, like we discussed earlier with the differential processing technique, that might not even be an option for some regions. So imagine that your objective is to have a precise centimeter, several centimeter level position precision, but you're operating somewhere in a remote Pacific area. That leaves you with PPP as the only available option in that case. But there are plenty of resources available that describe the fundamentals for PPP and some of those considerations in terms of different convergence times or different achievable accuracies, with some comparisons to conventional differential baseline processing. So yeah, I recommend anyone that's interested in the topic to review some of the links that are on the screen now. Some of them provide tutorials for how their specific software is doing their PPP solution, and some are more general. If you're really interested in doing your own, maybe more custom PPP processing, there are really good open source software options available in a variety of programming languages. So those are also a pretty good place to become more familiar with the technology in general. Yeah, thanks for the question, Heather. I wish I had a better answer for the ROI part.
Thank you, Brian.
I think, Tom, you had another question you'd like to ask. I think Brian, too.
Yes, thank you. So, Brian, thinking about the workflow for U.S. surveyors to use online positionings, in particular, what about the PPP services that are not going to produce coordinates in NAT 83?
Thanks, Tom. I have a slide prepared to hopefully address your question. The modernized National Spatial Reference System, modernized NSRS in the United States, is moving away from NAD 83. It actually aims to align to the International Terrestrial Reference Frame, ITRF, 2020 at a particular reference epoch. So you bring up a really good point, Tom, about PPP, because it's inheriting typically the ITRF reference frame from the satellites themselves, and it's all the computations are done at the measurement epoch or the mean measurement epoch. So that kind of leaves NAD 83 out of the processing chain. So there are always some transformation parameters or transformation utilities between reference frames that are provided by NGS. But fortunately, because of the decision for the modernized NSRS to agree with the ITRF, PPP offers a really great opportunity to enable that reference frame agreement directly. So that doesn't necessarily include the measurement versus reference epoch for those different frames, or any additional plate rotations that are being modeled and applied for matrif, for example, with the modernized NSRS. But it's definitely one step closer and reduces the processing complexity if you were to use NAD 83, for example.
Okay. I think, Muge, did you have a couple questions? Or
Only one more question. Jihye, what is the main advantage of PPP? Conversely, what is the biggest limitation of PPP?
Yeah, great question. So when we talk about this, the classic PPP, not the PPP real-time PPP service, I just want to differentiate between those two. So the classic PPP, by using standalone receiver and antenna, and then receive all this information and then do the processing, the biggest advantage is the cost, because you don't need anything else. Any subscription is needed, like you don't need any subscription, data service, or anything, because what you need is to just like pull your data out, pull your equipment out, and collect your data, and then do the processing later. So the biggest benefit is the cost, efficiency, and also you can place it anywhere, anytime, and without any dependency. So you can place it in the middle of ocean, in the middle of the desert. So that is the biggest advantage. Then still you can achieve like centimeter level of accuracy. But at the same time, the limitation is the convergence time. As we discussed earlier, we need for the high accuracy solution, we need the precise orbit and clock product, which cannot be provided in real time. So you may need of several days for the final product of this like high precision clock and orbit solutions. So the real-time application, that is the limitation. However, for the conventional surveying, or like a construction site, the surveying for the construction site that doesn't require the real-time solution, in that case, PPP could be the effective and efficient option. When we talk about the PPP-RTK, the service as a PPP, then so it doesn't have this limitation of this real-time operation. You can use this in a real-time operation. Still, it's relatively lower cost than the conventional like RTK or network RTK. But still, it requires the service subscription, and you still need to be in the service area. So that's the difference between those two.
Okay. I got another question, maybe for Jihye. for centimeter or even millimeter level accuracy, what type of data do we need? Do we still need to provide data for the atmospheric conditions, for example? It seemed like to really get down, listening to what you said and what Brian said, the critical part is you get that atmospheric information as well as maybe the geometry of the satellites and the local for you at the. So what are those data sets? Can you just clarify that for me?
Yeah, so it seems like we need a lot of information. As I just said, that there are different types of errors we need to tackle one by using different sources. However, the most important thing is the carrier phase observations and dual and higher frequency capability of the GNSS observations, like the capability of recording the GNSS observations. So that is the core part, that you need higher precision observation, and the multiple constellation GNSS could improve your solution greater than just a GPS only or a single constellation only solution. So these are the basic setting, but you don't need to worry too much about tackling each error source, because most PPP software engines has their internal computation and correction methods. Earlier Brian shared the different services and the online tools of PPP, so they already embedded their own algorithm. So how to calculate the tide effect from this sun and moon position based on the approximate location of your receiver and the time of the data collection. So these would be ready. One thing you may want to consider to achieve really high accuracy solution is the tropospheric delay or tropospheric effect. That could be further mitigated if you have the actual observations of meteorological observations of your site, like temperature, pressure, and humidity. Then you can accurately calculate the tropospheric effect at the moment of your data collection. However, it's less critical than others because, as I mentioned earlier, some atmospheric parameters like pressure and temperatures are pretty stable, that you can get relatively highly accurate hydrostatic delay models and mapping functions. And also, if you don't have the meteorological data measured from your data collection, but there's another option is you can use a so-called VMF, Vienna mapping function information that's provided by the Vienna mapping function data server. So I think their TU Vienna, the group, the research center, they calculate the near real time weather observations and provide the tropospheric Genius tropospheric delay model and also the mapping functions, I think with 6 hours of latency. And also there's a very similar model like GMF, it's like global mapping function that is pretty close to the Vienna mapping function model. That is empirical mapping function based on this numerical weather data. So these also provide a pretty high accurate solution. So even if you have your meteorological observations, then you may have the highest accuracies for your tropospheric delay mitigation, but the alternate options would be available by using the resources from the other data center, and also the PPP engine also included, or like most algorithms inside.
All right, thanks. That brings up another question. You talked a lot about with the weather conditions and maybe the geometry, and maybe this goes to both you and Brian. What about, and Brian, I think you mentioned this about how it degrades in tunnels and in urban canyons you talked about, and some other aspects. You had a slide up there. So we can see that those have a effect, and they will degrade PPP. Well, they'll degrade almost any kind of GNSS data. So how do we overcome that? And what can you speak just a little bit, and this is up to both of you, about ways of overcoming that? Is it augmenting this the PPP results with some other information, like if you're going through a tunnel or you're in the urban canyon, that you can do something?
Yes, that's a really good question, Dave. I did have a slide discussing some of those considerations, some of those factors, but one thing I didn't mention was that those are typically addressed with sensor integration, mainly inertial measurements, high rate inertial measurements. So when you do have a case where GNSS data are not reliable or maybe not even available at all, then the solution will follow that inertial solution more than the potentially noisy or unavailable GNSS solution. So those conditions are typically addressed just by that sensor integration concept.
And if I can add a little bit more, because they've mentioned the environmental factors that degrade this PPP solution, I would like to mention this the space weather condition, because the ionospheric delay is highly affected by the space weather, the solar activities and space weather, and the 2025 is the solar maximum year. So that in the last few years, we are experiencing really severe, like pretty frequent severe geomagnetic storm events. So that degraded GNSS solutions, like not just PPP, but most of these GNSS solutions significantly. So I have just a summary slide about from this what we from these recent publications on our research group. So actually, this is some of these figures showing. So actually, this is the KP index, that is the indicator of the magnetic storms during the during the 10th to 15th of May 2024. So there's like significant the storm events. It's like a G5 level that's extreme. The classified as extreme geomagnetic storms. And you see that during that moment there is like so here this is the ionospheric scintillation indicators indexes that I don't want to go into the details, but these scintillations create the signal interruptions and the scatters of the signals that dramatically affect the signal degradations and loss of luck. The lower part is the total electron content measured during these days, and the red is like predicted TEC, total electron content variations in the ionosphere, and the black is what's measured. And you see this during this significant weather event, space weather event, the expected, there's like big difference between the expected and what's measured. So that highly affects the PPP solutions, which is this lower right-hand side. So the bottom is the occurrence, and the upper one is the vertical error, vertical component of the PPP error solutions. And you see this while during the strong weather, space weather event, the vertical errors goes up to like almost 10 centimeter, which is not expected for the PPP, static PPP solution. So because of these unexpected space weather solutions, our PPP solutions could be significantly degraded to overcome maybe like some the scintillation indicators could be an option that we could exclude some of the signals affected by the scintillations for the solution. So there are different ways of mitigating these effects during the data collection. So that could be another aspect we can consider.
Great answer to the question. I appreciate you both. So we're winding down here, but I do want to, just in case anybody on our panel has some question that came up from basically some of the answers they get, I want to give everybody one more little chance if they want to speak up and ask a question before we close the session. I don't see anybody jumping up and down. So, well, we appreciate both of the speakers, and we thank the panel members for participating in this. And it was a lot of great information about PPP, and I know users will be out there very interested in trying to obtain more information about it. But thank you both for taking the time to do this, as well as the panel member. Appreciate it all. Thank you.
Thank you.
Thank you.